flow process of fluids through beds of solid particles will involve circulation of fluid through porous bed. This circulation of fluid through porous bed is what we call as fluidization. The common example of this circulation that takes place in processes are filtration and flow through packed columns, for example, the one used in distillation, absorption, adsorption, ionic exchange processes. In the case of filtration, particles are deposited in a filter medium while the fluid will passes through. And for absorption or ionic exchange, the fluid moves through a bed of solid particles, and these solid particles usually doesn't change its characteristics. And all of these processes are governed by the same law that we have looked into in the previous video, which is Darcy's law. And this Darcy's law is actually looking into permeability. And it says that the average velocity in a section of the bed is directly proportional to pressure drop of the fluid passing through the bed, and also inversely proportional to its thickness. So if the bed is thicker, then the average velocity would be lower or slower. Porous bed constituted of set of solid particles that are placed randomly, and to characterize this bed, few parameters are considered. The first one is specific surface or specific surface area, and for this specific surface area, it can be for the entire bed or for a particle. And the second parameter is porosity. If we look into specific surface area of the bed, so the bed is area of bed surface exposed to fluid by unit of the bed volume. If we want to look into specific surface area based on the particle, so it will involve actually ratio area of its surface, particle surface over the particle's volume. And when particles are not sphere, we use equivalent diameter. For equivalent diameter, for different shape, they will have a different numbers, and this equivalent diameter is actually diameter of sphere that would have the same surface area to volume ratio as the particle. Porosity, while porosity is actually particle bed that is not compact, and there are zones of free particles. And to define this bed of porosity or void fraction, we define as the volume of the bed that is not occupied by any solid material. And to describe this flow fluid through porous beds, we have a few equations involved. The first one, and this equation is actually correspond to the type of flow. For the first one is laminar flow, turbulent flow, and we do have the laminar turbulent global flow. And for a laminar flow, the equation is represented by Korsney-Kármán. And for turbulent flow, it will be represented by Burke-Plummer. And for laminar turbulent global flow, it will be shown by the equation derived by Ergun and Chilton-Kolber. So if you can see here, this is a schematic showing how the fluidized beds will look like. So it will have a fixed bed, and this bed of solid particles resting on perforated bottom. So you can see this is the perforated bottom. This is the perforated bottom of a tall container, and the fluid is forced upward with low flow rate, fixed particles, and fixed volume. So we do have a fixed volume. As the flow rate increase, the pressure drop rises until it reaches the point where the pressure drop through the bed will exceed the weight of the solid bed itself. And at this point, the bed starts to expand, and this is what we call as fluidization point. If the flow rate is increased further, the bed will continue to expand and the particles of bed begin to move freely and randomly. And the pressure drop remains nearly constant despite the increasing of this flow rate of the fluid. So if you can see here in this graph plotted between log of pressure drop versus log of superficial air velocity, if you could see in zone 1, the log of pressure drop, the relationship between pressure drop and air velocity is in straight line. This is because the fluid circulates and the fluid circulates, and this circulation velocity gradually increase at low velocity, so the beds will remain static and there's no changes in height or changes in volume. Therefore, the pressure drop plotted therefore we're going to get this relationship whereby the pressure drop versus the air velocity is in a straight line. And if we keep on increase the flow rate, we can see here the velocity and pressure drop is still proportional to each other. However, here the particles already begin to separate, but they are still in contact, and we can see it will have a smaller slope compared to the first area. And once they reach here, this drop, this phase is what we call as continuous fluidization. Within this range of velocity where bed is fluidized, once the particles have been fluidized, velocity of fluid in contact with particle is higher than the velocity of the fluid that has passed through the bed. This phenomenon causes particles go up and back to the bed instead of being dragged by the fluid. So this condition, it will look like the bed is being boiled, or we call this as boiling beds or discontinuous fluidization. And then when particles are actually dragged, two-phase circulation occurs. The first one is and this is where we call it as continuous fluidization, and continuous fluidization is basis for pneumatic transport. So application of fluidized beds is when we in individual quick freezing (IQF), agglomeration of particulates, coating of particulates, and rapid heating or cooling. This is where we can see the fluidized beds process. So we've mentioned earlier that to characterize the fluid velocity in fluidized bed, we do have three equations to represent it, and these equations are based on the types of flow, laminar, turbulent, and we also have a global flow. So minimum fluid velocity required for fluidization is VMF, and this can be calculated by equating the pressure drop with apparent weight of bed. The various expressions have been proposed for calculating this pressure drop, and the most commonly cited is Ergun equation. And Ergun defines a Reynolds number for a bed spherical particles of equal size S. So this is Reynolds number. Remember, equation for Reynolds number is rho Vd over mu. So this is the general Reynolds number equation. And in order to understand this fluidized bed, we're going to include the porosity of the bed. So Egan's equation for the pressure drop per unit bed height is when we consider the height of the bed or the thickness of it. The first terms of Egan's equation represents the pressure drop due to friction between fluid part and particles, and the second terms is pressure drop due to sudden changes in direction. So this is the first term, due to friction. That's why we do have a velocity here. And the second term is due to sudden changes in direction. For Reynolds number less than 10, the second term is negligible. So this second term, due to sudden changes in direction, is negligible. Hence, we're going to focus only on the kinetics, on the front peaks. Expression for the minimum velocity for fluidization is derived as shown here. In most food applications of fluidization, the particles are small and light, and this makes the condition of the Reynolds number less than 10. In this case, the Kozeny-Kármán approximation is used. The minimum velocity for fluidization is then calculated through this equation. This is an example of situation to show how fluidization can be calculated. For the design of fluidized bed freezer, it is desired to calculate the minimum fluidization velocity, which is Vmf of P's in air at negative 40 degrees Celsius. And suppose the P's are uniform spheres. The data, which is diameter given, are diameter of P's 5 mm, particle density of P's, then porosity of the P bed at rest, and for air at 40 degrees Celsius, they give the density and as well as the viscosity. So this one, we will use this equation. And it will give, just plug in the values and you give a minimum fluidization velocity of 14 meter per second.